Let us discuss on the topic of fast decoupled power flow. In the case of Newton-Raphson power flow, the calculation of this Jacobian matrix is highly computationally expensive. So now we make lots of assumptions and approximations in order to simplify this Jacobian matrix and make this computational process of power flow analysis faster. That also compromises on the accuracy of the solution, but it gives you a quicker solution. So now in this Jacobian matrix, the kind of assumptions we consider are primarily two. One is we neglect the conductance, that is G value, and then we also assume that the angles are smaller. As a consequence of assuming that the angles are smaller, we'll have the sign of the angular difference to be very close to 0 and the cos of that angular difference to be close to 1. So now if you try to substitute these assumptions in the elements of the Jacobian matrix, here we can see the expression for the elements of the Jacobian matrix. In that, the first Jacobian block, if you consider that the Jacobian matrix as the block diagonal of 4 matrices, then in the case of J11 in this matrix, when you neglect the conductance, that is G value, then you can see that this particular expression can be neglected. And similarly, here also we can see that this particular expression can be neglected. And then here also we have this to be neglected, and then this expression also be neglected. And after considering that the values of G are neglected, you can also look at the real and reactive power expressions to be given as these equations. That's where we have removed the G values. And the second assumption that we have in fast decoupled load flow is that angles are smaller. When you consider that the angles are smaller, you can see that this particular value will be neglected. And again, even this particular value will be neglected. Apart from that, we also see that this PK, the real power injection, can also be neglected, which means that in this assumption case, your values of this PK will be approximately equal to 0. So because of that assumption, you see that the first term in J12 is almost neglected, and the second term is also going to be neglected. So that is where you can consider that the J12 can be fully neglected after these assumptions. And if you look at the J21 also has its first two terms being neglected. In the diagonal also you have a PK, which also considered to be neglected because the second value is GKK, and here also you have GKK, so that is anyway being neglected. So now you see that the off-diagonal Jacobian matrix elements are close to 0 when you consider that the conductance is neglected and angles are smaller. Because of that, in this Jacobian matrix, you see that this part can be neglected and also this particular part can be neglected. So as a result, our resultant Jacobian matrix will look like this. The Jacobian elements corresponding to J12 as well as Jacobian elements corresponding to J21 will be fully neglected, and then the elements corresponding to J11 and J22 will be something like this. So now we try to further simplify these elements of the Jacobian with an assumption that the voltage profile that we have taken is a flat voltage profile. If you try to look at that assumption, that is when you have your JKK and JKK in the second block diagonal J22 and J11, that is where you will consider that the Vk and Vj are correspond to flat voltage profile. So then you can consider that voltage as Vk itself. Then this will become Vk square, and this is already Vk square. So you can take that Vk square out. Then you will have the first term as the sum of the all Bkj's minus Bkk. Now what does this mean? This is somewhat similar even in the case of J22 also. Now what is the meaning of sum of all Bkj's? Now sum of all BKJs is somewhat similar to the elements of the admittance matrix. Now, if you expand that sigma j is equal to 1 to n BKJ, then that is nothing but BK1, BK2, BK3, and so on, BKN. So now, that value, if you try to look back into your admittance matrix, that is nothing but the sum of all elements in a row or in a column. Now, when we have observed that admittance matrix, a sample 3 by 3 matrix, if you look at it, then sum of all elements in one column is nothing but y10, and sum of all elements in second column is y20. That is, when you add all the elements corresponding to a row or a column in an admittance matrix, that gives you the value of the shunt admittance connected at that bus. So now here, this sum of all BKJs, where J is varied from 1 to n, is nothing but BI0, whereas BI0 is nothing but the shunt susceptance connected at that bus. Now, if you look at the shunt susceptance in relation with respect to the diagonal elements in the admittance matrix, that is where you have this expression where the first value is BI0, small BI0. Now you know that that small BI0 will be much smaller when compared to BKK, so we neglect that BI0. As a result, we'll have this expression as minus VK square multiplied by BKK itself. So similarly, we'll also have the diagonal element corresponding to J22 being simplified with the same assumption. Combining the assumption that we neglected conductance, and also we considered the angles to be very small, along with the flat voltage profile assumption that we have taken, the resultant elements of the Jacobian matrix will become very simple. So this will be the Jacobian matrix elements, and you also now know that there is no coupling between the angles and the reactive powers, and no coupling between the voltage and the real powers. So as a result, this is what will be the ultimate relationships that we use in the power flow solution using the fast decoupled load flow. Now, if you try to put the J11 elements in a matrix form, that's where you will try to see that this is going to be B dash multiplied by theta is equal to V inverse of delta P. Now, V inverse, V is nothing but a diagonal matrix where all the diagonal elements are corresponding to the voltage at a bus. Now, that inverse of a diagonal, when it is multiplied with delta P, that is when you will see that this is going to be delta P2 divided by V2, delta P3 divided by V3, and so on. So that is what we call it as the modified delta P. So actually, our delta P is nothing but delta P2, delta P3, and so on, delta Pn. The modified is nothing but it is normalized with respect to the voltage at that particular bus magnitude. And now, this delta P modified is completely related to the angles through B dash. So whereas that values of B dash are nothing but the elements of an admittance matrix itself by neglecting the real parts or the resistances, and that is of this size. And similarly, we'll also see that the reactive power related expressions, update expression, is from the J22 elements, that it is corresponding through B double dash. B double dash is a subset of B dash, but B double dash is nothing but the elements or the subset of the B dash where we consider only the elements from the NG plus 1 to N, that is only for the load buses. So this is where if you wanted to find the update for delta theta, or nothing but the angle update as well as the voltage update, if you know the values of the delta P modified and delta Q modified with the assumed values of the voltages or initial guess of voltages and angles, then you can update that initial guess using these particular equations where inverting B dash and B double dash is the only thing that is complicated in every iteration, which we'll try to solve utilizing the LU decomposition in our fast decoupled load flow. Now, if you look at a very simple example of a 3-bus system that we have solved in the previous cases, that this is our admittance bus matrix. Now, what is B dash and what is B double dash for us? What are these two matrices for this 3-bus network? Provided our admittance bus matrix, now we know that B dash is nothing but the susceptances that are from the second bus to the nth bus. assuming that our first bus is a slack bus. So in this particular admittance bus matrix, now consider that your first bus is a slack, then you have second bus as the generator bus, and the third bus is a load bus. That's what we have considered in our previous example. That means that B dash is nothing but starting from the second column, and also it also starts from the second row. So the elements in this particular region will be your B dash. And when it comes to B double dash, this is nothing but the susceptances that starts from Ng plus 1. Now the number of generators in our case is 2. Now Ng plus 1 is nothing but 3. So that means that you have the elements corresponding to B double dash are only this. So this total matrix is B dash, and only this matrix is B double dash for us. So that's how you will be directly getting the values of B dash as well as B double dash from your admittance bus matrix. And also I should consider that you have neglected the conductances. So this is what is the way that you have your admittance matrix, split that, then you will be able to get what is your B dash. And if you just start the elements only from the Ng plus 1, then that is what is going to give you B double dash. So consider that this is very small, only one element corresponding to B double dash. That's what makes the fast decoupled load flow solution to be very, very simple. So LU factorization is something that makes the inversion of a matrix in fast decoupled power flow to be very simple. Now let's say you have a 3 by 3 matrix and you wanted to find the LU factors for that. That is also a very simple process. Suppose you have an A matrix and that is being represented as L and U, then you can see that the product of these two matrices is something like this. Now it is very straightforward for us to calculate the elements of this L and U matrix from these relationships itself. It is very clear from these equations that L11, L21 and L31. So all these three, L11, L21 and L31, these three elements are directly related to A11, A21 and A31. So that means you can say that your values of L11 is nothing but A11 for us. And similarly, your value of L21 is equal to A21, and your value of L31 is exactly equal to A31. And after getting the three elements of the lower diagonal matrix, then you can see the next element in your matrix, that is L21, U12 plus L22. Now, in order to get that, you need U12, but you can see that if you look at this particular equation, that is your A12 is exactly equal to L11 multiplied by U12. That also gives us that you can get your value of U12 as A12 upon your value of L11. Whereas you already have the value of L11 and you can substitute and get the value of U12. Similarly, you can also get your U13 as your value of A13 upon your value of L11. So that's where you'll be able to get the value of U13. And now you can use the diagonal element that we have here and get your value of L22. So if at all you wanted to get the value of L22, then you can write down your L21 multiplied by U12 plus L22 is equal to A22 for us. Now L21 is already available for us. U12 is also available for us from here, and then L22 can be calculated as L22 is equal to A22 minus L21 and U12. That's where you will be able to get the values of L22. Now once you have your L22 value, then you can go for the element in this particular position and try to get your value of U23. So because you can see that your L21 and U13 plus L22 U23 is equal to A23 for us. Now in this particular equation, L21 is already available for us and U13 is already available for us. L22 we calculated here and U23 is to be calculated. So you can get the value of U23 from here. So U23 is basically A23 minus L21 U13 upon L22. So that's where you'll be able to get U23. So just if you start from your first element in the LU product matrix and proceed with one after the other element, then you will be able to get your elements corresponding to all other L and U matrices. If you try to calculate all the elements of L and U matrix using the relation between A matrix and LU product, then this will be the ultimate relationship between the LU matrix elements and A matrix elements. And you can also generalize that and say that the elements of L matrix can be obtained through this particular expression, and elements of U matrix can be obtained through this particular expression. And we need to follow a sequence. You cannot calculate all the L values from the beginning, or you cannot calculate all the U matrix elements at once. So you need to go in a sequence from the calculation of first column elements and then the first row elements in U, so that you'll be able to get the values of L and U matrix through the formulas that we have here. That is how we can get the elements of L and U matrices.